So this next bit is actually the last part of the permutations and combinations topic that was the very first extension 1 topic that we looked at last year, which is binomial probability. But in order to handle it, we needed to know the binomial theorem, hence why we didn't look at it last year. Okay, so binomial probability. The event has only 2 possibilities, which when you think about it, most things can be broken down to 2 possibilities. Either it happens, or it doesn't happen. And then you just keep repeating that event. Then the probability distribution. Well, if I do it once, there we go, A or B. We'll say A has a probability of P, B has a probability of Q. If I do it again, well, if I did start off with A, I'd branch off to AA or AB. If I started with B, I'd go to BA or BB. So the probability of AA would be P squared, then PQ, Q squared. Branch off again. So if I'm going down the AA line, then I'd go AAA or AAB. Then if it was AB, ABA, ABB. Then if it was BA, then it'd become the probability of a sheep. And then I'd go BAB. And if it was BB, we go BBA or BBB. And the probability is there. As we look at these probabilities, they're quite familiar. AAA, AAB, AABA, AAB, B, ABB, ABA, ABB. Okay. Now the probabilities for those, and again we see the pattern emerging. They're exactly the same as our expansion in a binomial, but the question is how many of each do we have, and that's where the binomial coefficient will come into play. So how does this work? So one event we said was P or Q. 2 events, P squared. Now if I'm not concerned about the order that it happens, then the probability of getting an A and a B would be 2PQ. Again, if I look at 3 events and I'm not concerned the order, then it's starting to become a little bit more obvious what's happening here. In fact, it is just the terms of the binomial expansion. And there's 4 events. Now, what that means is the general term in a binomial expansion is also the same as the probability of however many. So if I've got an event, I'm going to repeat it n times. I know the probability of X happening is P, and the probability of it not happening would be Q, which also would be the same as 1 minus P. Then the probability that X will occur exactly K times, but I don't care the order, will be, and there you see it, it is just the general term of a binomial. NCK, probability of happening to the power of K, probability of it not happening to the power of N minus K. So our notation there, probability X equals K simply means X will occur exactly K times. So we've got a bag, 30 black balls, 20 white balls. 7 drawings are made with replacement. Of course, this is only going to work if the probability is the same every single time. So it has to be with replacement. What's the probability of drawing all black? Well, I'll use the binomial probability idea, but I suppose we didn't really need to for this one, because every time is going to have a probability of 3/5. So of course we end up with 3/5 to the power of 7. But from a binomial probability point of view, we're saying 7C7, which is of course 1. 3/5 to the power of it happening, 7 times. 2/5 to the power of it not happening, 0 times. So we get our answer. So there's an unsimplified answer, and there's the actual answer itself. Well, what happens if we just want 4? So probability X equals 4, 7C4, probability of happening to the power of 4, probability of not happening to the power of 3. So that's 7C4, 2 to the power of 3, 3 to the power of 4, over 5 to the power of 7. A lot of the times we do just leave it like that. I suppose it depends on how big the numbers are. 7C4, 2, well, how big is that? Oh, that's not too bad, that one. Okay, election comes along. We know 30% of the voters favour Party A. We're going to interview 5 voters randomly. Probability that 3 of those favour Party A. Okay, so X is going to be the number favouring Party A. So probability, well, I suppose I should have written A equals 3, but 3 A's. 5C3, probability of happening to the power of 3. Probability of it not happening to the power of 2. So there's the unsimplified answer, and there's the actual answer itself. Majority favour A. Well, if the majority favour, then either 3, 4 or 5 will favour. Now I've just got to add those 3 together. So the denominator is 10 to the power of 5 for all of them. Then you've got that beautiful expression on top. For some reason in the middle one I decided to put a dot multiplication in there, but there we go. Okay. At most 2. If you think about it, at most 2 is the complementary event to majority. So rather than reworking it all, I could still use that idea of 1 minus the complementary idea, which we've already worked out. So 1 minus that, 20,923. Alright, this is an interesting one. HSC question. So there are 5 matches on each weekend of a footy season. Megan's taken part in the competition. She'll get 1 point if she picks more than half of the winning teams in a weekend. Otherwise, 0 points. Pretty tough rules, that competition. Probability that Megan correctly picks a team that wins in any game is 2/3. Show that the probability that Megan earns a point is 0.7901. So in order to earn a point, she must pick correctly more than half. More than half. So I'm going to say X is the number of matches picked correctly. We want X to be more than half. So 5 games, 3, 4 or 5 correctly. And probability of picking correctly was 2/3. So 2/3 to the power of 3, then 4, then 5. 1/3 to the power of 2, then 1, then 0. Making sure we've got our binomial coefficients there. And when you bung that into a calculator, sure enough, comes up 0.7901 to 4 decimal places. Okay. Hence, find the probability that she earns 1 point every week of an 18-week season. So now, I'm going to say, well, Y is the number of weeks Megan earns a point. Okay. So probability that Y equals 18. And the probability of Y happening, we just worked out, was 0.7901. So 0.7901 to the power of 18, 0.01. Find the probability she earns at most 16 points. So at most 16 points. Well, it's going to be easier to work out 17 or more, especially since we've already worked out 18, and subtract that from 1. So probability for 17, probability for 18, subtract from 1, and we get 0.92. 2007. Large city, 10% of the population has green eyes. What's the probability that 2 randomly chosen people have green eyes? So just 0.1 times 0.1, 0.01. That's not a binomial probability question. What's the probability that exactly 2 of a group of 20 randomly chosen people have green eyes? So X is the number of people with green eyes. We want X equals 2. So 20C2, probability of happening to the power of 2, not happening to the power of 18, 0.285. What's the probability that more than 2 of a group? Well, again, it's that complementary idea. So I'll subtract 2, 1 and 0. That gets me 0.32. Okay, so we'll now go back to our permanent and common chapter where there's 10J and we can finish that topic now.